So today I'm going to tell you about ab initio Eliashberg studies on anharmonic, anharmonicity and zero-point motion and retardation effect in superhydrite. So my name is Ryotaro Arita from University of Tokyo and Riken Center for Emerging Matter Science. So doesn't. Okay, so this is reference of my talk today. So first is our recent review articles on superconducting hydrides. And the second is ab initio studies for lanthanum H10. And the third one is studies on hydrogen sulfide. Okay, so let me start with my talk with a slide from Lilia Boeri, who was supposed to give the second talk in this session, but unfortunately, she cannot join this session. So, so I'd like to start with her question. So, near loop temperature superconductivity in high pressure hydrate. How did we get there? So, as was nicely reviewed by Professor Hemre in the previous talk, so it does start with physical intuition by Ashcroft in 1968 or 2004. But recently, thanks to the development of the techniques of crystal structure predictions or ab initio superconducting calculation or developing the techniques of high pressure synthesis. So now new superconductors can be predicted, including chemical formula, stoichiometry, or synthesis pressure, and indeed synthesis. And for the part of crystal structure prediction is already discussed by Professor Hemre, and since time is limited, so I'm going to show just one slide. So one very successful example by Liu and Professor Hemre in 2017, case of lanthanum HX. So here, so this figure shows entropy for various lanthanum HX, the so-called convex hub. So if we look at this plot, for example, in the case of lanthanum H6, the enthalpy is higher than the line connecting lanthanum H5 and lanthanum H8. So we can say that this structure is not stable. But on the other hand, in the case of lanthanum H10, so this enthalpy is lower than the line connecting lanthanum H8 and H2. So we can say that this lanthanum H10 is stable at 150 gigapascal. And also in the 300 gigapascal, so lanthanum H10 is also stable. And then we can study the structure of compound. And once a structure is determined, then we can step forward to ab initio superconducting calculation. And so in this talk, I'm going to introduce recent progress in the ab initio superconducting calculation, focusing on the treatment of retardation effect or phonon anharmonicity or zero-point motion. So let us first discuss the retardation effect. So let me start with the introduction to Migdal-Eliashberg theory. So it is a self-consistent perturbation theory. And in the NAM-Golkov formalism, we consider the lowest order dressed phonon and dressed Coulomb contribution to the self-energy. So this is the phonon Green's function D, and G is electron phonon coupling constant. And this is the screened Coulomb interaction we see. And so when we solve this, the so-called linearized gap equation, the Migdal-Eliashberg theory, technically we have one problem. So namely, So if we look at the dynamical structure of phonon-mediated attractive interaction, so the typical energy scale is just omega pH and the energy scale of phonon, so about 0.1 electron volt. But on the other hand, in the case of screened Coulomb interaction, the energy scale of the screened Coulomb interaction is much larger. As large as the bandwidth, sometimes 10 or 20 electron volt. So the energy scale is very different. And when we consider to solve this equation at low temperature, to cover the wide range of the screened Coulomb interaction, we need to introduce many numbers of Mazubara frequencies. Otherwise, we cannot describe the two interactions. But it is numerically formidable task. So we usually follow the argument by Morel-Anderson and derive an effective equation for the low energy part. And then the screened Coulomb interaction, so mu, is renormalized and mu becomes mu star, what we call Coulomb pseudopotential. But however, these parameters usually introduce substantial uncertainty in the quantitative estimate of TC, because we have some ambiguity to estimate this factor. So usually we treat mu star as an empirical parameter. And then we can not calculate, perform a free non-empirical calculation TC. And to overcome this problem, there are two approaches. So one is the so-called superconducting DFT. So it is an extension of density functional theory, originally formulated by Hadi Gross and his collaborators. And there we extend DFT and we introduce anomalous density on top of normal density. And then the Hohenberg-Kohn theorem is extended to be a one-to-one correspondence between two types of potential and the two types of density. So this is atomic potential, and this is a pair field, and normal density and anomalous density. And then the Kohn-Sham equation becomes the Kohn-Sham-Bogoliubov-Dojan equation. And so we have two types of potentials and the two types of density. And this is the exchange correlation functional. And from this Kohn-Sham-Bogoliubov-Dojan equation, we can derive the gap equations. And the form is very similar to that of Migdal-Ehrenberg theory, but and this is the kernel of the gap equation, which can be obtained by taking a functional derivative of exchange correlation functional and Hartree terms with respect to anomalous density. And it should be noted that the quantities in these equations are all static. I mean, there's no omega dependence. So the numerical cost to solve this equation is very cheap. And in these papers, Hadi Gross and others constructed a very nice exchange correlation functional, FXC, for phonon-mediated superconductors. So they considered three types of diagrams, and so it should be noted that these are closed diagrams, so there's no omega dependence. And this is a normal Green's function, and the phonon Green's functions, and the anomalous Green's functions. And this is a screened Coulomb interaction. So they are all can be calculated from first principles. And so although this quantity does not have omega dependence, but it still has a Kohn-Sham state dependence. And if we look at the contribution of phonon-mediated attractive interaction in this column, so we see that this part is finite only for states in the vicinity of the frame level, in the energy scale of phonon. But on the other hand, for the contribution of Coulomb part, almost state independent. So the state dependence is very different. And from this difference, we can consider the retardation effect automatically. So this is, so the numerical cost is not so expensive, but still we can consider the retardation effect. And so this is some benchmark calculation for elemental aluminum and niobium. And so this is a gap function and the temperature. And we see that the experimental TC of aluminum or niobium are very accurately reproduced. So without introducing any adjustable parameters. But the one problem in SCDFT is that, so it's based on the constant perturbation theory. And here, this Green's function, we employed the bare Coulomb interaction. So this part, we don't have self-energy correction. So the mass enhancement effect is not considered self-consistently, and sometimes the TC is underestimated, as I will discuss later. So, so now then we consider again to solve Migdal-Eliashberg equations from first principle. And if we look at these equations, we see that it's basically the convolutions of pairing interactions and the Green's function. And so if, although it has many numbers of Matsubara frequencies, but if we can do a Fourier transformation efficiently, then we can solve this equation very efficiently. So the question is how to perform this Fourier transformation from the Matsubara space to imaginary time. And for this problem, recently we developed a new scheme based on the so-called intermediate representation of the Green's function proposed by Shinaoka and others. So the idea is the following. So we start with the spectral representation of the Green's function here. And this is the kernel. And we do the singular value decomposition of this kernel. And then we have U and P. And here we look at this U of tau. And in this paper, Shinaoka and others found that if we expand the Green's function in terms of this U, then so this is a very efficient expansion of the Green's function. So we need very few numbers of bases. So this is the demonstration. So this is the exact Green's function. And they show that if we introduce just 6 bases, then we can reproduce the tau dependence of the Green's function very accurately. Of the Legendre polynomial. And then, so we can reproduce, we can represent the Green's function with a very few numbers of bases. And then, so should be noted that this U, the base function, U of I omega or U of tau, so these are both can be pre-computed and stored in the library. And once we determine the coefficient GL by a linear square fitting, for which the numerical cost is not so high. And once we have this coefficient, then we can calculate G of tau or G of I omega very efficiently. And then, so using these techniques, we found that this equation very efficiently. And so now we can perform a self-consistent calculation for Migdal-Eliashberg theory equations, considering the retardation effect. So this is a calculation for H3S. And so which demonstrates the importance of the self-consistency. So here, this is self-energy of the electrons. So this is phonon-mediated attractive interactions. And if we calculate this sigma and perform one-shot calculation using the Baire-Goulding functions, then the mass enhancement effect is overestimated, and then the TC is underestimated. But if we perform self-consistent calculation, then the mass enhancement effect is treated properly, and the TC can be calculated more accurately. So this is the recent progress on the calculation of the retardation effect in the molecular area Schwarz theory. And then let us move on to phonon aharmonicity. And as was discussed by the previous speaker, Professor Hemley, so in the case of superconducting hydride, when the system experiences structure transitions, we often have a very strong harmonicity. So this is the phonon calculation based on the standard harmonic approximations for Lansalam H10 at 150 gigapascal or 200 gigapascal. And we see that there are many negative phonons, which means the system is very unstable. And then, so we decided to go beyond the harmonic approximation and consider the anharmonicity. So here we start with the anharmonic Hamiltonian. So this is the harmonic part, and this is an anharmonic part. So UN is given by these equations. And here U is a displacement of atoms, and this phi is the force constant. And if we represent UN with a normal coordinate, then UN becomes like this. So here delta is unity when the sum of Q becomes 0. And this phi is the force constant in the reciprocal space. And in the second quantization formalism, the displacement of atoms is a sum of creation or annihilation boson operators. So the Hamiltonian becomes like this. So the harmonic terms H prime. Here we have more than 2 boson creation or annihilation operators. So the harmonic part represent the interaction between phonons. And to treat this harmonic term, so there is a theory which we call self-consistent phonon theory, which was originally formulated by Futon and others. And here we have a nice review by Tadano Tsuneyuki. And so in this formalism, we mimic the free energy of the original Hamiltonian by an effective harmonic Hamiltonian. So this is the effective Hamiltonian, harmonic Hamiltonian, and this is the dressed phonon frequencies, so which is actually is unknown, and we are going to determine this frequency. And to determine this frequency, we use the so-called Gibbs-Bogoliubov inequality, and we minimize the right-hand side part. So we call it F prime. And for this can be minimized by taking a derivative of F prime with respect to the dressed phonon spectrum. And then, we can derive on self-consistent equations. So this is the dressed phonon equations. And recently, Tadano and Tsuneyuki formulated a very efficient algorithm to determine this force constant, exploiting the fact that this is a sparse matrix. And then we can, by solving these equations, we can determine phonon frequencies. So this is a so-called SCP, self-consistent phonon theory. And also there's another method to treat phonon harmonicity, which we call stochastic implementation for self-consistent harmonic approximations. And recently for ransom H10, we performed calculation for SCP and SSCHA, and we confirmed that both methods gives almost the same results. And so let me show the results for ransom H10. And so this is the result for harmonic approximation, and we have many negative modes. But if we go beyond the harmonic approximation and take account of the an unharmonic effect, then we obtain this green curve. So now we don't have negative modes, and by considering harmonicity, we have phonon dispersion, which does not become negative. And using this dispersion, we can calculate the Elias-Berg functions and calculate the electron phonon coupling constant lambda. And this is a plot of lambda as a function of pressure and logarithm average of phonon frequency is for ransom H10. And we found that, so we see that, so electron phonon coupling constant becomes as large as 3.5. So it's a very big value. And also the energy scale of phonon frequency is 1000 Kelvin, so which is also very high. So large electron phonon coupling and the phonon frequency, so they are usually do not coexist. But in the case of ransom H10 and high pressure, these can coexist, and this is a very good situation for high TC superconductivity. And using this Elias-Berg equation or phonon frequency electron coupling, we perform the Migdal Elias-Berg calculation and calculate TC as a function of pressure. And so we see that the agreement between theory and experiment is very good. And this is the results of SCDFT, superconductor DFT. As I mentioned, in the case of SCDFT, the mass enhancement effect is not treated self-consistently, so TC is a bit underestimated. And so the case of Migdal Elias-Berg theory, so it can also reproduce the isotope effect. So now, so TC is reproduced accurately without introducing any empirical parameters. And in fact, in this calculation, we assume that the system takes this very symmetric structure. But now, so finally, I would like to comment on the 0-point motion. So if we calculate the entropy based on the Born-Oppenheimer calculation. So in conventional calculation, we assume that the Born-Oppenheimer approximation is good. But if we follow this Born-Oppenheimer calculation, calculate entropy, and then we found that this symmetric structure, which is very good for superconductivity, is not stable. Can be stable when we apply sufficiently large pressure. So 150 or 200 gigapascal, this symmetric structure is not stable and can be distorted. And when the structure is distorted, and then the density of states at the Fermi level becomes small. So when this structure is symmetric, then we have a very sharp one-hole singularity in the vicinity of Fermi level. This is very good for superconductivity. But this structure, so if we follow the standard Born-Oppenheimer approximation, this structure is stable only when the pressure is very, very high. But if we consider the zero-point motion means if we sum up the phonon frequencies, so half of h over omega is the contribution of zero-point motion. And if we consider the quantum effect, then we found that this symmetric structure can be stable down to 150 gigapascal. And in fact, the high TC superconductivity was observed under 200 gigapascal. And we believe that this quantum effect is important to explain why this symmetric structure survives under 200 gigapascal. Namely, so lanthanum H10 is a quantum crystal which is held via quantum effect. Okay, so let me summarize. So we introduce recent progress in the ab initio irreversible calculation, focusing on retardation effect, phonon harmonicity or zero-point motion, and we can now calculate transition temperature of superconducting hydride very accurately, and which can be used in the future material design. So thank you very much for your attention.
Maybe could I ask a question? Just your self-consistent phonon approximation. So my naive feeling, your description was that the parameterization of an effective harmonic oscillator will be temperature dependent. No, if I think about an anharmonic system. So I'm confused that you do a t=0 projection and then extrapolate to a very high temperature. How can I understand?
This theory, self-consistent. So we so exploiting the fact that the phi is at a very sparse matrix, and then we calculate this force constant and solve this equation.
But isn't that effectively temperature dependent based on the phonon occupancy, you know, at finite temperature?
Phonon distributions.
Oh, okay. So I just wasted 2 minutes of everybody's life. I think, thank you. But maybe there's a better one coming.
I don't know. So I have two questions regarding the electron-phonon coupling. One is how, if it's clear that the large amygdala approximation still holds for the for these large pressures, and the other one is does the electron-phonon coupling needs to be renormalized due to the anharmonic effects here?
You could the question clearly?
The first question is the validity of amygdala approximation, yes, right?
For these very high frequencies.
Yeah. For this problem, so it doesn't stop. Sorry. In this paper, so actually in this paper, we studied the validity of amygdala approximation and consider the first correction to the amygdala approximation, and found that amygdala approximations slightly suppress DC. And on the other hand, so in the standard amygdala HVAC theory, we do not consider the omega dependence of screen-Coulomb interaction, and the distribution of plasmon enhance TC, and these two effects are balance, and eventually the amygdala calculation, the amygdala irreversible calculation gives TC agree well with the experiment.
The second part you want to push?
The second part was what?
Yeah, I'm actually curious if anharmonicities will change electron phonon.
So he wants
yes. in this paper, we also studied how this electron hole coupling can change. And so this effect also has some effect. Yeah.
Okay. So last gasp.
Yeah, in order to avoid this pseudo potential, pseudo potential, due to this screen pooling interaction, I'm curious how it's calculated.
So the question was about
Pseudo potential?
Coulomb pseudo potential and how you calculated that the screen Coulomb interaction.
A screen Coulomb interaction is a random phase approximation. We calculate the random phase approximation and calculate the so-called W, and took the matrix element.
Okay.
Can I ask a question?
Sure. Wherever it's coming. Oh, yes, please. Fantastic.
Emily, yeah, very nice talk, just beautiful work. But I have a comment about the experiment. We clearly see in the case of lanthanum H10, the phase going from cubic to rhombohedral with respect to the lanthanum sublattice. So that clearly stands out in the diffraction. We don't see, of course, the hydrogen sublattice, which is obviously highly quantum and anharmonic, but the diffraction data show a rhombohedral phase. So this doesn't wipe out the rhombohedral phase. It could preserve higher symmetry with respect to the hydrogen sublattice. Do you have a comment?
We have not yet calculated that phase, but I agree that it's a very interesting future problem. Yes.
Because you imply that the rhombohedral phase doesn't exist because because of the expanded stability field of cubic, but we clearly see it in diffraction.
Yeah, actually, we are now performing more comprehensive calculation of this quantum calculation for various structures. And yeah.
Thank you.
Okay, so since it's locally dinner time and this very modern conference we're doing, I wanted to thank both of you. Thanks very much for dialing in from Japan.